Okay, so let's start. So today we are going to do okay 11.4, that is comparison test. Comparison test. Okay, so let's first see what is a comparison test. So let's say that we have a sequence. So if we have a sequence like this, B sub n is greater than or equal to A sub n, and all the sequences are, all these terms are positive terms. Here, this means it's a big sequence, and this is, let's say, it's smaller sequence. So now we are comparing two sequences where one sequence is larger than the other sequence. Okay, then we are going to establish a technique from this idea how to find whether a series is convergent. Okay, if there is two sequences. So let's say, so the idea is this is called a direct comparison test. So the first one is if the big series, that means n to infinity b sub n is converges, we write it like this as a arrow into just a finite number. So this means it converges. Then the small series also converges. So this is called a direct comparison set. So if we just show, so I will write again in notation, the small series also converges. So if I let's draw this and visualize. So this means, so suppose that we have a big sequence. So that means, let's say the big sequence is this, and it is converges. So converges means it appears to a horizontal asymptote, right? So let's say this is M. This is a big series. Big sequence. So this is, let's say it is sequence. Okay, and it converges means, like I said, it has a horizontal asymptote. Then a small sequence, let's draw with a different color. Small series means it is less than the big series, so it will appear like this. Big one, and this is smaller one. So if big series is convergent, you see by the graph, the small series is definitely converges because it also has a horizontal asymptote of M. Okay, that's the idea. Okay, so then what is the other part, the second one? And don't forget, so if you have this, important one is important. But remember, if small series convergence, we can't say about the convergence of the big series. The vice versa is not true. If the big series is convergent, small series can be convergent. That's true. But the other way around, we cannot say it can be convergent, it cannot be convergent. So if a small series is convergent, we can't say about the convergence of the big series. It can be convergent or divergent. The second one we can say, the second direct comparison test is if small series diverges, so that means A sub n, this is diverges, that means series will, you will get infinity or negative infinity. Then what can we say? Then if a small series is divergent, then big series diverges too. So that means the series of B sub n, it diverges too. If I draw this, okay, I'm gonna have a picture for this. So the same thing goes to here also. Note or important, the other way is not true. So if the big series diverges, you can't say the small series diverges. Series small series diverge, because it can be diverges or it can be convergence. So the vice versa, it's not true. Okay, so let's do an example. Example. Four plus 3 to the power n. So we have to check whether this is convergence or divergent. Convergent or divergent. Okay, so we are going to use the basic comparison test. So that means we need a new series, right? To compare, we need a new series. So what can we do is, so we have this series, 4 plus 3 to the power n. We can so if I write it in the, so here you see in the denominator, you have 4 plus 3n. So if we get rid of this 4, we will get a series like this. So if we get rid of this 4, we will get a series like this. 3n. Right? So what can we say? So which series is bigger and which series is smaller? What do you think? So let's say this A, let's say this is B. What do you think? Which series is bigger than the other? A is bigger, B, Mallory says B. What do you think? Others? B is larger, right? Why is B is larger? What do you think? What is the reason where B is larger? Small dividing minus, yes. Yes, so small, so if you have the bigger the denominator, so I will write it as D. If denominator increases, then you get a smaller fraction. So when the denominator is bigger, that means if you divide a number by a very large one compared to the other, then your the fraction will be decreasing. Okay, so here 4 plus 3 to the power n is bigger than 3 to the power n. Okay, because we are adding a number here. So when you take the reciprocal, this sign flips and we get something like this. Okay, so then we can say A is less than or equal to B. Okay, so let's say this is your Bn and this is your A sub n sequence. Okay, so that means if I write it, Bn is greater than or equal to A sub n. Okay, now we are going to compare this series. Okay, now we are going to talk about, we are going to check the convergence of the divergence of our new series that we produced. So that is 1/3. So to check whether this is convergent or divergence, we have to check whether this part, we have to check which technique that we are going to use to show this is convergence or divergence. What do you think? Which technique we can use here? Can you recall what how do you say, William, it is convergence? Which technique that you used? So here we can see R is, yes, very good. So this is a geometric series, right? Here, because we can write this series as 1/3 to the power n. Okay, then the ratio, common ratio is what? Common ratio R is 1/3. So this is a geometric series. Okay, if the common ratio is less than 1, then we already know we have a technique. If the common ratio is less than 1, then the whole series is convergent. So then this whole series is convergent. So that means the big series. So this is our big series, right? Because here we use this part. So this is our big series. So then what can you say about the small series? Therefore, our small series is this. It is, yes, good color. It is also convergent, because the big series is convergent, then the small series is also convergent. This is by direct comparison test that we learn. Test. This is also convergent. Convergent. Okay. Okay, so the idea is whenever they give you a series, you have to think a little bit and make a new series. Okay, so here what we did, we get rid of these 4 and created a new series. And then we are going to compare that series, and we are going to find that that series is convergence or divergence from a technique that we learned. And then we can say about the other series whether it is convergence or divergence. Okay. Any questions? This question? Did y'all understand? Don't worry, we will do more questions, then you will be fine. Okay. Okay, so then let's do another one. Now let's see. Now you have to think a little bit what series we are going to compare. N to the power 3 plus 5. Whether this is convergence or divergence. Can you all take some maybe 2 or 3 minutes and think of a series that we can compare this series with? Yomil said 1 when cube. What about others? I see many correct answers. Yes, very good. So I'm going to get rid. I saw many correct answers. So here I'm going to get rid of this 5. Okay, then I'm going to create a new series. Yes. So let's me. Okay, so let's write the new series. So I have 1 over n to the power 3 plus 5. So why am I get rid of this 5? The idea is when n is very large one, that means if it is infinity, this 5 is insignificant, right? Whenever you add a small one, it's insignificant. Let's say you have a 100,000. You add a small number, it's insignificant. Okay, that's the idea. Okay, so we have this, and we have 1 over n to the power 3. Okay, so we are going to compare this series with this one. Okay, so what do you think is bigger? Is it A or is it B? A or B is bigger. What do you think? B, right? From the same idea we used in the previous one. Because if the denominator is greater, your whole fraction is less. So here you have n to the power 3 plus 5. Here you have only n to the power 3. So that means we can say we can have an inequality. A is less than or equal to B. Okay. Okay. So now the next step is we are going to compare this one. We are going to find the convergence or divergence of this series and compare with the with our other series. Okay. Okay. Now let's write that series that we are going to compare. So we have 1 now into the power 3. So what do you think? Which technique that here? Kyle said, Kyle have an answer. What about others? What series we are going to use? What technique we are going to use? P series, right? We are going to use P series. So what does P series means? So P series. So if you have like this n to the power P, if P is greater than 1, then your whole series converges. If P is less than equal to 1, your whole series diverges. Okay, so here what is P now? What is P here? 3. Okay, so 3 is greater than 1. So then by P series, we can say this whole series converges. Okay, then what can we say about this series? So our bigger series is convergent. Then what can we say about our smaller series? Converges. Okay, by the direct comparison test, our small series, that is 1 over n cube plus 5, also convergent. Okay, so this bigger series is convergent. When bigger series is convergent, the small series is also convergent. Always remember that by a graph, then you will be fine. Okay, then you will not be forget about that theorem. Okay, so let's do another one. Example. What about this? Convergent or divergent? So can y'all think about a series that we are going to use? Kiyomi said, okay, I have one answer. Skylar. Good. Others, can you try for maybe take some 1 more minute and think? So when you're finding this new series, you have to think this new series we should be a series that we can use the any technique that we learned previously, and that we can show the convergence or the divergence of that part. Okay. Yeah, I see many correct answers. So here also, what we are going to do is the same idea we used in previous one. So when n is infinity, it's a very large one. Then this plus 4 is insignificant. Okay. So if we compare this, we can get rid of that 4 and we have this series. So let's now think about whether which one is greater than the other. So same idea. If we have A, this is A, B. It's the same idea we have used in the previous two. So what can you say about which one is bigger? B is bigger series. So we have this. Now we are going to compare our new one. So let's take the new series. So let's write this part in terms of exponent. So this is same as series 1 over n to the power 1/4. Okay. Okay. Now which technique we are going to use? P series. Okay. P series. Yes. Same idea we used in the previous one. We can use P series, right? So by P series, so what is our power then? Now here it's 1 over 4. So this is less than 1. Then what can we say about this series? If it is less than 1, it is divergent. Okay. So then by P series, we can say that this whole series is divergent. Then what can you say about our smaller series? What do you think? Whether it convergent or divergent? So I will write, is it convergent or divergent? I mean, the bigger series, that is this. We can't say anything. Emanse can't find base of. Yes, very good. So we cannot say anything about the smaller series because this even though the bigger series is divergent, the smaller series can be divergent or can be convergent. Okay, we cannot use the direct comparison test. So the answer is, so we cannot say, so we can't say anything about it, and we name that is as inconclusive. Because the direct comparison test says only if the small series is divergent, then the big series is divergent. Okay. Let's do another example. I hope you understood. Any questions up to here? This one? This question, did you all understand, everyone? Why it is divergent? I mean, why it is inconclusive? Okay. Okay, so let's do another one. Okay, can you all try this one? Is it convergent or divergent? So you have to think about series that we are going to compare. I want all of you to try this one, everyone, okay? Colby, Brice, are you all here? Peter, are you here? Peter and Brice. Caleb says, let's see. Okay. Brady, good. Micah, okay. Yeah, I see many of you have the correct answer. Very good. So let's see what we are going to use. So what do you think? Which series we are going to use as for comparison? So which series we are going to use? Yes, Amani, yes, very good. 2 to the power n, 7 to the power n. So same idea we used in the previous one. When n is infinity, that means if the n is very large number, then we can get rid of this 8. Okay, so we have without 8, we have 2 to the power n and 7 over there. Okay, and then what do you think which is bigger? So from previous one, yes, Alexis Williams. So this is the series we took is bigger than the other series. Okay, now we are going to write this in terms of a series that we already know. Okay, so we can write this one. This is same as 2 over 7 to the power n. Okay, then what is this series? Geometric series. Okay, so this is a geometric series. Good job. So this is a geometric series. So then we can use the idea that we learned in the geometric series. So here the ratio, we have to consider the common ratio. So the common ratio here is 2/7, okay, which is less than 1, right? So if it is less than 1, we can say about the convergent or the divergent of the series. So what do you think? By the geometric series, since this is less than 1, since R is less than 1, then the series is convergent. So since 1 and this series is convergent. So that means our bigger series is convergent. Then what can you say about the smaller series? By the direct comparison test. So by direct comparison test, we can say that this series, the smaller series, is convergent. That is convergent. Okay, I see many of you have already now know what we are doing. So let's do another example. Our new example is this. Ln n over n, convergence or divergence. So think of a series that we can compare this with. What do you think? Before proceeding, can you tell me a series that we can compare this with? Ln or 1 over n. Okay. Okay, so let's think. Let's see what is the new series that we can introduce. So here you have to notice that when n is increasing, that means if you get a very large amount, so if you consider the numerator and denominator, numerator is ln, the natural log n. This is getting, I will write it in this term. So when n goes to increasing, when n is increasing, that means when n goes to infinity, n increases. That means the denominator increases faster than the natural log. So that means we can compare this. So this is the idea. So when n increases, that means when n goes to infinity, when it is very large amount, this part is increases faster than the numerator. Okay, so we can compare the natural log to, so natural log, remember this idea. So natural log is greater than 1 when n is greater than equal to 3. You can check this idea. Okay, so how do we check? So when n is equal to 1, we know the natural log of 1 is just 0. Okay, when n is equal to 2, the natural log of 2 is just check it's something 0 something 0 point something. Okay, so when n is equal to 3 only, this is greater than 1. Okay, it's 1 point something. Okay, so this idea we are going to use. So when n is getting very large amount, that means we can use this inequality. So when n goes to infinity, therefore we can use the natural log over n is greater than or equal to 1 over n. So we can now write as a series. Okay, so I have already written the answer. So this part is bigger than this one because of this inequality that we use. Okay, now we are going to compare this series. So what is this one? I have mentioned this is a name for this kind of series. What is the name for this kind of series? Harmonic, right? Very good. Kiyomin, very good. And Riley, yes, very good. So this is harmonic series. Is harmonic series. So harmonic series, what do you think? Is it divergent or convergent? It's divergent. Very good. So it is divergent. We can use why it is divergent. This is divergent. Harmonic series are divergent. Why it is divergent? We can use the P series, right? So when P series, if we use P series, here P is equal to 1. So we learn that if it is P is equal to 1 or less than 1, that series is divergent. So then by P series, this whole thing is divergent. Then what do you think about the bigger series? If the smaller series is divergent, then what do you think? It diverges as well. Okay, so if the smaller is divergent by the direct comparison test, so by direct comparison test, our larger series is also diverges. Okay, so this is another kind of example. So let's do another simple one. Example, what do you think about this series? Plus 5n square. Is it convergent or divergent? So what is the series that we are going to compare this with? 1 over n squared. Okay. It's, yes. Yes, I see many correct answers. We are going to compare this with n over n squared. Why? Let's say, so we have n plus 5. I see many correct answers. N plus 5 over n squared. So here, this is, we are adding something to the numerator. So that means this is greater than n over n squared, right? It's just a simple idea. If the numerator is greater, then the fraction is also increases. Okay, because n plus 5 is greater than n. Okay, so then we are going to write this as a series. Okay, now I'm going to write this one where I'm going to simplify this. We can write by simplifying. This is 1 over n, right? Because here it is n to the power 1. So we can just cancel 1 n. So we end up of getting 1 over n. So like the previous one, this is again a harmonic series. So again, this is divergent. So then what can we say about the bigger series? If the smaller one is divergent, then by direct comparison test, yes, test, we can say the bigger one is also divergent. Very good. Divergent. Okay. So let's write one final example for this type, and let's then move on to a new one. I'm doing more examples because sometimes students get confused how to introduce a new series. So let's do this one. Okay, what do you think the new series would look like? One over square root. Yes, Jai. Yes, yes, very good. I see many correct answers, Riley. Yes, very good. Yes, so we are going to get rid of this 5 again, the same idea we used. So I'm going to write it as, because square root n to the power 4 is greater than the square root 4. So we can say the same idea we have used. If the denominator is greater, that means the fraction is less. Okay, so I'm going to write this now as a series. Power 4. Okay. Okay, so what can you say about the new series? Larger. Yeah, it is larger. Okay. Is it convergent or divergent? Convergent. How does it convergent? Why it is Emma says divergent. So if you give an answer, can you tell me for why? What is the reason? Kyla says, okay, okay. Okay, so we are going to write this is same as when you take the square root of n to the power 4, that is same as n squared, 1 over n squared. Okay, again we are going to use p series because we have a power. So p is 2 here. 2 is greater than 1. Okay, so then p series, we can say that this part is convergent. Then what can we say about the smaller series? And by direct comparison test, I will just write DCT. Since the bigger one is convergent, then the smaller series is also convergent. Yes, very good. So it is also convergent. Okay, so this one is also convergent. Okay, so this is called the direct comparison test. So what did we do here? So whenever a series is given, we introduce a new series. Why we are introducing a new series? Because we don't know any technique to solve this series. We don't know any technique to use to show that this is convergent or divergent. So we are introducing a new series so that we know the new series is convergent or divergent by a technique we already know. It can be P series, or it can be, we can use geometric series or any other series that we learn. Okay. Okay, so the next one is called the limit comparison test. Comparison test. Okay, so let's see what is limit comparison test. So consider two sequences. First, let's write and I will explain. Consider two sequences. Sequences, that is A sub n and B sub n. Let's say both are positive. Let's say both positive and greater than 0. 0. Okay. So the limit comparison test means if n approaches to infinity, A sub n divided by B sub n, if you get a finite number, this is a finite positive, and also remember it should be positive number, positive finite number. Why it is positive? Because we took the A sub n, B sub n are positive. That's why the answer should, when you take the quotient, then answer should be also definitely be positive. So positive finite number. Then the conclusion that we get is so the series, if you have to I got a message. What is it? Can you go up someplace? Yeah. Okay, Alexis. Or do you want me to go up more? Let's get it. Okay, so let's wait for this. Let me know if you have, after taking all the notes. Okay. Everyone, are y'all have taken all the notes up to here? Okay. Okay, so this is the new part, limit comparison test. So I will explain again. So if you have two sequences, both sequences should be positive, and that means greater than 0. And when you take the quotient of these two terms, that is a sub n divided by b sub n, when n approaches to infinity, if you get a positive finite number, so you have the two series because you have two sequences. These are the two series. We can say it's both converges or both diverges. Both diverges. So when we are doing the example, you will understand. The idea of both converges and both diverges means here also we are comparing to two series. And if we have one series that we already know from a previous technique with whether it is convergent, and then we are going to find this part. We are going to show the limit when n approaches to infinity, the quotient, we get a positive finite number. If you get a positive finite number, we can say both series are convergent. So I'll do an example, but this is the idea. Okay. But from this one, can you recall a test that we used? What is this? When n approaches to infinity, uh, if you get a number, if you get a so don't get confused by the divergent test, okay? Because we did the divergent test if we have limit n approaches to infinity. So I will recall again the divergence theorem. When n approaches to infinity, if we show this is equal to 0, okay, then we said the series, this is divergent. Only this is the conclusion we get. That's the divergent test, but we don't need that here. But that's the divergent test. I just recall it. Okay, so let's do an example for this limit comparison test. Okay. Oh, sorry, I forgot to write here. So a note. So if let's say if we establish, that means we introduce a new series, and that series is that Bn converges, then the series A sub n is also converges if limit goes to infinity, n approaches to infinity, A sub n is a finite number, finite positive number. If it is diverges, A sub n diverges, then the series B sub n has to diverges as well. So just write the note, then we'll understand this by an example. So the example is n squared n to the power 5 plus a. So use limit comparison test. comparison test. So is it convergence or divergence? Okay. Okay. So this is just one series. So to use the limit comparison test, we need another series. Okay. So what is the series that you can use? From the previous one, direct comparison test, what is the series that we can use so that that series, if you use a technique that you already know, you can show that it is convergence or divergence. What do you think that you are going to use? Just forget about this new word, limit comparison test, and just figure it out by direct comparison test. In the previous one, what is the series that we can take to compare? N squared to the, yes, n squared to the power, n squared over n to the power 5. So we can get rid of this 8 and we can introduce a new series that is n squared over n to the power 5. So this is same as what? This is same as what? Because we have power, so this is same as what? It is because we can use the quotient rule of power rule, so we can write this is same as n to the power 3, right? We can cancel because this is same as this is like this. So we can cancel 2n. So we have 1 over n to the power 3. Okay. Now, what do you think about this series? Which technique that we can use to show? Now we have done several times. P series. Okay. We can use P series. So by P series, what do you think? By P series, it is convergent because P is 3 and that is greater than 1. So this series is convergent. This series is convergent. Okay. Okay. So we know this series is convergent. Okay. Now we have, but we are not done yet because we need to know what happens to our this series. So we are going to use the direct comparison, a limit comparison test to this. So if we can use the limit comparison test, that means if one series is convergent, we can show this one is also convergent. Okay, how to use a limit comparison test? We have to check when n approaches to infinity, a sub n over b sub n. So let's say this is a sub n is n squared over n to the power 5 over 8, and b sub n is 1 over this. Can you all check? Can you all take the limit of this one? So now check. Now check. Limit n approaches to infinity, a n sub b. So instead of writing like this, just write your quotient like this. N approaches to infinity, a sub n multiplied by 1 over b sub n. Then you will, then it is easy to visualize. It is easy to think how we are going to cancel all the things. So just practice to write this quotient like this. Okay, so let's write, because it's the first question I'm going to do with y'all. So when n approaches to infinity, our a sub n is n squared over n to the power 5 plus 8 multiplied by 1 over b sub n is this, that is 1 over n cube. So this is same as n cube over 1, this whole thing. So when n approaches to infinity, n sub 5 plus 8 multiplied by n cube. Because why? 1 divided by 1 over n cube means if you if you change it to multiplication, this right hand side flips. So this will become n cube over 1. So this is n cube. That's why it is, I get 1 n cube. Okay, so this is equal to n approaches to infinity, n to the power 5, n to the power 5 plus 8. So now this is your limit knowledge. What can we do now here? How are we going to solve this? One over 8. Okay, yes. So we can divide, because this is the highest power. Okay, we can divide everything by n to the power 5. All the terms by n to the power 5. Okay, so we will have 1 over 1 plus 8 over n to the power 5. Okay, then when n approaches to infinity, what happens? When n approaches to infinity, what happened to this 8 over n to the power 5? This whole thing is 0. So we will have 1. So we have n approaches to infinity, an sub bn is equal to a positive. Now this is a positive finite number. Okay, then we can use the limit comparison test. So because we showed that limit when n approaches to infinity, the quotient is a positive finite number. So then what can we say about the series? Because since this is a positive finite number, it is by limit comparison test. It should be both should be converges. Oh, sorry. It should be both should be converges or both diverges. But here in this example, we showed that this series that we introduced, because 1 over n to the power 3 is converges, then our series that is n to the power 5 plus 8 to the power 2 is also converges. Okay, so what did we do here? So we found, what did we do? So when a series is given, we are introducing a new series. Okay, and then this new series, from a previous technique, we can show that this is convergent or divergent. Okay, so here in this example, we show that the new series is convergent. So we keep it aside. Then we are going to find when n approaches to infinity, a sub n divided by b sub n, this quotient, we are going to check whether you will get a positive finite number or not. So if we get a positive finite number, what can we say from the limit comparison test? Both series is convergent. Because we showed this series is convergent, then we can straight away say that our series is also convergent by limit comparison test. That's the idea. Okay, because this is the first example, you might get confused, but you will be fine after doing some other examples. Okay, so let's do, are you all okay, everyone? Okay, we'll do another example. This second example. Three to the power n plus 5. Is it convergence or divergence? By limit comparison test. Okay, so you have to check by using the limit comparison test. So what is the new series that we are going? So the first question that you have to ask is, what is the new series that we are going to introduce? And it should be a known series that we can, like a known technique that we can use. What do you think? 1 or 3. Yes, good. So we are going to introduce the new series is so the other series or the new series we are going to introduce is 1 over 3 to the power n. Okay, so what is this series? We have done the same question. So what is this series? Can you identify? Geometric series. So this is a geometric series. Okay, so since this is a geometric series, then we can use this is what is the common ratio and what do you think? Is it convergent or divergent? Convergent, yes, very good, Jai. So it is convergent because the common ratio is 1 over 3. So 1 over 3 is less than 1. Okay, so then by the geometric series that we learned, so this series is therefore, so this one is convergent. Now we keep this aside. Now we are going to find, so let a sub n is equal to 3 to the power n plus 5. B sub n is equal to 3 to the power n. Okay, so now check. So this is the first step, finding the other series is it convergent or divergent? And the second step is you're going to find when n approaches to infinity, what happened to the quotient. So I'm going to write this as like this, an multiplied by 1 over b sub n. Okay. So can you all do this and tell me whether it is, what do you get? Do you get a positive finite number or not? It's a positive one. Yes, one. Yes, good, very good. So, yes, William. So here, let's write it. A sub n is 1 over 3 to the power n plus 5. Kyla, okay. So multiply 1 over. Now, b sub n means 1 divided by 3 to the power n. So then, by can write this as 3 to the power n plus 5 multiplied by 3 to the power n. This same as limit n approaches to infinity 3 to the power n, 3 to the power n plus 5. And then because we have the same 1 here, 3 to the power n, I'm going to divide all the terms by 3 to the power n. Plus 5. 5 also 3 to the power n. So you will get 1 over 1 plus 5 over 3 to the power. And then we just take the limit. And we can say when n approaches to infinity, what happened to this part? What do you think? This is just 0, right? Because remember, if we have something like this is 0. This is the theory that we use. So it is 1 plus 1 over 0. Just 1. Okay, now this is a positive finite number. Then what can you say about the other series? I mean, the question series. What can you say about? Because we have one series convergent. So what can you say about this one? By the limit comparison test? It is convergent. It is also convergent. Convergent. Why? Because of the limit comparison test, both should be convergent. By limit comparison test. I will just write LCT for that. Okay. Let's do another example. Okay, up to here, are you all okay? Anyone? Everyone? Okay, did you take all the notes up to here? Lee, you're silent today. Okay. Okay, so let's do another example. Example, new one is this 1 over square root n squared plus 2. Okay, now think with is it convergence or divergence? Now think of a new series that we can use. So by now you should be able to identify like a series that we are going to introduce, because we have done several examples now. Yes, very good. So yes, so I think all of you are okay now. So we can get rid of this 2, and then we can introduce a new series as, so this is the series that we have. So the new series, we can say the other series is, we can use this one. 1 over square root n squared. Okay, so 1 over square root n squared is same as, if we take the square root of n squared, this is same as 1 over n. Then, is it convergent or divergent? It's divergent because it's a harmonic series. Also by P series, this is divergent. Okay. Then if we show, so if we show that limit n approaches to infinity, a sub n divided by b sub n is a finite positive number, then we can say about, then both series are divergent. That's the idea that we are going to prove. Okay, so now let's find whether we get a positive finite number. So let's say a sub n is 1 over square root n squared plus 2. B sub n is 1 over n. Okay, so when n approaches to infinity, then 1 over n squared plus 2. This is 1 over n. Can you all find whether you get a finite positive number or not? Is equal to 1. Yes, we have one answer. So let's start. So we can write this as, yes, okay. So I can write this as, this is equal to limit n approaches to infinity, 1 over square root this one into 1 over n. So this is same as, I write it like this, and multiply by 1 over bn. That's why this here square root n square plus 2 multiply this whole thing is like n. Okay, then what can we do? We can divide both, I mean all the terms by n, all the terms by n. So the numerator you will have 1 over, when you divide n squared plus 2 by n, not, so this is same as, because n is same as square root of n squared, right? So we can write this as n squared plus 2 over n squared. Okay, it's the same thing. Then when we divide both by n squared, you will get 1 plus 2 over n squared. So this is 1 plus 2 over n squared. Okay, so now take the limit when n approaches to infinity. So when limit n approaches to infinity, then this whole thing becomes 0. Now, then this is equal to 1. So we have, when n approaches to infinity, a sub n divided by b sub n is equal to 1. Then what can we say about the other series? Because we showed this is divergent. Then what can you say about this series? By the limit comparison test? By, yes, Kyla, good. By limit comparison test, Mallory, good. So it is divergent. So infinity plus 1 over square root n squared plus 2, it is divergent. Okay. So by this example, we can conclude the comparison test. Okay, all the comparison tests we have done. So like this is the end of 11.4. Okay, so this is a new technique to show whether the series is convergent or divergent. Okay, the comparison test. We can use either the direct comparison test or the limit comparison test. Okay, any questions here? This section, are y'all okay, everyone? So if I give a random quiz, can y'all do now? Okay, okay. So don't worry, I'm not going to give a random quiz now. Okay, so let's do the next section, and that is called 11.5 alternating series test. So this is another kind of test that we can use to show the series is convergent or divergent. Okay, so we have now lots of tests, but now this is a different kind of test. So let's see what kind of a series that you will get for here. So alternating series will look like this. -1 to the power n. This is just an example. 1 over n. Okay, so if I write this, in terms of, so what is the first term when n is equal to 1? What is the first term? What do you think? -1, okay. What is the next term? Can you all write just 4 terms? Half, okay. third term. What is the third term? When n is equal to 3, negative 1/3, right? Okay, so when n is equal to 4, then what is 1/4? Now you will notice, you can notice. So if you have just without this sign, if you just forget about this sign, we have a negative here, negative. If you don't have this sign, that means you have 1 plus 1/2 plus 1/3 plus 1/4. What is this series? This is just this one, right? 1/3, I mean 1/n. What is this series? Harmonic series, okay? If you don't have this sign, it is a harmonic series, and you know harmonic series are divergent. But because of the new parties, if you have a sign here, this means -1 to the power n. This denotes your sign. This represents your sign. You might get a negative or you might get a positive value. Depends on your power. If power is odd, you will get a negative value. If the power is even, you get a positive value, like here. Okay, this is called a alternative series. So sometime one you have negative, in the second term you have a positive. In the next term you have a negative, again positive. So negative, positive, like that. So it's alternative. Okay, so this is called a alternating series. So the sign is alternating. So if the sign is alternating, then we call that series. So we call that series alternating series. Alternating series. So if it is an alternating series, we are going to use the alternative series test to check the convergence or the divergence of the term. So let's see what is alternative series. So we have to check whether alternative series is convergent or divergent. Is alternative series convergent or divergent in this question? So that's a question we have to find whether this alternative series is convergent or divergent. Okay, so let's see what some other type where alternative series will look like. So alternative series, sometimes it will look like this. So that means n approaches to 1, -1 to the power n, a sub n. This is your sequence, that is a sub n, or also sometimes it will look like this, n plus 1 to infinity, -1 to the power n plus 1. It's the same thing, and a sub n. So these are called alternative series. Okay, so here the a sub n is a sequence, And also this sequence is positive. Is positive. It is greater than 0. 0. An should be greater than 0. That means because only from this part only the sign differs, but other than that, your A sub n should be a positive one. Okay, so let's see what is alternative series. So to use alternative series, two conditions should be satisfied. Should be satisfied. So what are the two conditions? So the first condition should be it has to pass divergent test. What is divergent test? I recall in the first couple of minutes. So what is divergent test? If limit when n approaches to infinity, your A sub n is equal to 0, so this is what we have to show. We have to show that limit when n approaches to infinity, A sub n is equal to 0. What is a divergent test? Divergent test means if limit approaches to infinity, remember if we show that this is not equal to 0, we can say that this series is divergent. Okay, remember you asked then what happened if the series is when the limit approaches to infinity, A sub n is equal to 0. Then you ask what happened, is it convergent or divergent? So this is the technique we are going to use. If it is equal to 0, what happened? Is it convergent or divergent? So if it is 0, and then the second condition is sequences should be decreasing. Okay, so what is sequence is decreasing? We did this in the previous chapter. So what is sequence is decreasing? The second term, the next term should always less than equal to the previous one. So this is called a sequence decreasing part. So we need to show these two conditions to use the alternative series. Okay. Okay, so let's do an example. Example. So this is the last example for the day. If you have negative n to the power n, so same one we use with the start where we started the example. So this is the example we started. So we need to check whether this is divergent or convergent. So here, remember always, you have to take negative 1 to the power n in just like one term. And here, this is called the A sub n. Don't write A sub n with this part. Okay. So always, because A sub n should be a positive term, this is 1 over n. This is called the A sub n. Okay, now let's check the conditions. Can you all check when n approaches to infinity, what is A sub n? Zero, right? This is zero. Okay, so that means, so series, we say pass the divergence test. Divergence test. Okay, because if this is not equal to zero, then we can say the series is divergent. But since this limit is equal to zero, we say inverse, this is pass the divergent test. Okay, then the second one, we need to check that whether this is decreasing. We need to show that this is a true statement. Okay, so just substitute what is A sub n plus 1, that is 1 over n plus 1, less than equal to 1 over n. Is this a true statement? Yes, right? This is a true statement because remember we did in the beginning, if denominator increases, your fraction is decreases. So here the denominator is greater than n plus 1 is greater than n. So 1 over n plus 1 is less than 1 over n. Okay, so this is a true statement. So therefore, this sequence is decreasing. So since we satisfy these two conditions by alternative test, this series is convergent. So this is convergent. So here you notice, so if without the sign, if without this part, then this is a harmonic series. Harmonic series is divergent. But here we have negative 1 to the power n. That means it is an alternative series. So this is convergent by using the alternative test, alternative series test. Okay. I don't think I have time to do the, yeah, maybe we have time. Let's do one more example. Okay, this is easy. It's easy. So, because we have time, let's do another example. Can you all tell me whether this series is convergent or divergent? 2n minus 7. Convergent or divergent? What do you think? Is it convergent or divergent? Yes, very good. William, Mason, very good. You guys are, everyone, you are doing great. So this is, so what is A sub n? A sub n without this sign part we are writing. So 5n plus 3 over 2n minus n. So to use the alternative test, we need to find what do we get for limit when n approaches to infinity. So what do you get here? We can divide, yes, 5 over 2. We can divide everything by n, right? By limit knowledge we learn. So we can divide everything by n. 2n divided by n, 7 over n. Then we get 5 plus 3 over n, 2 minus 7 over n. So when limit approaches to infinity, this whole thing becomes 0. This is go to 0. So you get 5 over 2. Now this is not equal to 0, right? So what is this? If limit n approaches to infinity, a sub n is not equal to 0. So this is divergent test, right? Remember, if we show that the limit when n approaches to infinity, it's not 0, then so this doesn't pass. This doesn't pass the divergent test. I mean, doesn't pass the divergent test. So pass the divergent test means it should be equal to 0. So by divergent theorem, this series is a sub n. This series is convergent. This series is divergent. Divergent. Okay, so we cannot use the alternative series because we found that this is equal to 0. Okay, so alternative test fails because we found that this is not equal to 0. Okay, I will stop here. Let's do more examples from alternative series tomorrow, and we'll start another topic tomorrow. Okay, that's all for today. See you tomorrow. Bye. Have a good day, quiz 5. Yes, quiz 5 is due 19 tomorrow. Not tomorrow, day after tomorrow. Okay, Alexis, I have to go now. Can you send me an email? I will try to
Yeah, that's fine.
Okay.